Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Founded or co-founded at the Ember Corporation, which you're going to talk quite a bit about today. And the company has been actually one of a few small startups, has been working on the forefront of wireless sensor networks and the applications for that. Rob completed his PhD thesis with at MIT Media Lab. Right. And before that, Rob had worked in many different places, including a few places in Silicon Valley, Lucasfilm, Stanford AI Lab, among others. And he also had quite an eclectic interest, and I think you're a musician and worked for Grateful Dead as a recording engineer, and very interesting some acoustics, which probably will be another topic not going to be covered in this talk. But with that, I'll have Rob talk about wireless embedded networks.
Great. Thank you very much. I generally like to find out who I'm talking to first. So who here would characterize their interest in being more about the markets and the ecosystem, and the other choice is going to be in the technology? So markets and ecosystems, show of hands. Yeah. Okay, good. Technology? Got it. I know where I am now. Okay. I'm going to talk about two things, and I've actually split the talk up. I'm going to talk a little too much about Ember, because as I was talking with Feng this morning, I have a bit of an agenda here, and I'll be very explicit with the agenda. Ember's been in the business of making commercial embedded wireless network systems for 3.5 years. We have customers. They are shipping in quantity. I sit on the 802.15.4 standards boards. Our company works very actively with the Zigbee Alliance. I also go to the Berkeley Nest retreats. We've gotten DARPA funding. David Tenenhouse of Intel was on my thesis committee, so I stay close with this whole community. And part of my agenda today is to say I don't see enough overlap between the TinyOS, Moat, Berkeley world and the 15.4 Zigbee commercial application world. So one thing I'm encouraging is that there's more cross-pollination. Another thing is really, I want to figure out, I'm one of the founders of Ember. I care a lot about it. It's a company that's grown over 50 people, so it's gotten serious. And I feel like I'm, carrying this very precious, delicate thing forward. And I want to make sure it doesn't break on the way to being successful. So one thing I'm keenly interested in is, does it make sense for Ember and Microsoft to be doing something together? And that's an open question we'll just leave in the air and we can discuss later. I'm assuming that I don't have to spend a lot of time talking about why the term sensor network bugs me. Sensor networks gives you the idea that you have a one-directional network that's gathering data towards a central collection point. In almost every single application I can name that our customers work with, bidirectional communication is absolutely necessary. And the popular press misses that. Some of the algorithms, the routing algorithms, tend to ignore that. So that's something else we can talk about as much as you want. But what I want to talk about today then is really what's Ember about as a company, what's the technology that goes behind this and powers it, give you some sense of what's going on in the market itself. What is the ecosystem going on in the commercial world? And also give you some teasers about some cool technological tidbits that just haven't turned up yet in research papers. And also do a live demo for you. Questions before we get going? Things that you want to make sure I cover? Okay. And feel free to jump in. This is I call this the Chatty Cathy slide, because you pull the string on my back of my neck and I recite the following facts about Ember, right? We make wireless embedded networks. These are the little tiny devices that go into the Internet of Things. Our focus is on OEMs, because we're really focused on selling not to the end user, but to the people that manufacture this into their products. And we look for the high volume ones that will ship by the millions. We have already gotten design wins. We have a very specific definition of a design win in over 60 customers. A design win in our book means they've not only bought our developer kit and attended the developer classes, the developers seminars for how to develop these new stuff, but they also have to show that they've allocated internal resources of the company, engineering staff and budget, to take a product to market. The nice thing, the really gratifying thing, is the breadth of markets that we're seeing adopt the technology. We're seeing in home automation, building automation, security systems, homeland security, asset tracking and management, industrial automation, medical products, lots of things. I will touch on 4 specific ones later on here. The thing that distinguishes an embedded wireless network from any other kind of 802.11 network or even a Bluetooth network is that humans are not generally in the loop. This has to be unimpeachably reliable without humans doing something to it. If you are at Starbucks and you're on their wireless LAN and you don't have a good connection at your table, you will move 3 inches to the right to get a better connection. If you are a flow meter on a 10-ton tank, you do not have this option of moving 3 inches to the right. So there's a real premium on making systems that are reliable day in and day out without humans touching it. We were founded in 2001. We're a spin-off from the MIT Media Lab. We had initial funding even before co-founder Andy Wheeler and myself graduated from DARPA in the guise of the Sensit program, which some of you may have heard of. A lot of that was how you do self-organizing mesh networks for battlefield and situational awareness. We work very hard with standards bodies. In the commercial world, I say there's 2 big drivers to this whole market. One is Moore's Law. If you build it out of silicon, it will get exponentially cheaper over time. If you look at if you plot out the cost of radio modules, I'm seeing something on the order of a factor of 10 reduction in cost every 4.25 years. You want to plot that out. The other driver is sometimes called Metcalfe's Law. Just the networking affects itself. The more things that join into a network, the more valuable it is to join the network because there's more things on the network. Coincidentally, Bob Metcalfe is on our board. He recently became chairman, and also he became a venture capitalist just in time for him to take us to Polaris as his first portfolio company 3.5 years ago. So right now we have 53 employees. Our main office is in Boston. We bought a silicon design team in the UK out of Cambridge Consulting Labs, and now they work for Ember designing low-cost, low-power, really great radio chips. We are privately funded. We've got $28 million in the bank so far. For those that care about the names, Polaris, Grand Banks, DFJ New England, DFJ ePlanet, RRE Ventures out of New York. A little starting money from State of Ventures, raised state of analog devices, and as I said, Bob Metcalfe. Questions about the company? Here's a little bit about ZigBee and 15.4. If this is really old hat to everybody, just stop me. First off, people wonder what the relationship is between ZigBee and 15.4. And the quickest way to describe it is very much like the relationship between 802.11 and Wi-Fi. All the 802 standards define a MAC and a PHY, the physical layer and the medium access layer for how you share the airwaves in the wireless space. That's necessary but not sufficient for interoperability between different manufacturers. So in the 802.11 world, Wi-Fi exists so that a card made by one company will talk to a base station made by another. And that requires protocols well above the MAC and the PHY layer. An analogous thing holds true in 15.4. 15.4 is a low-power, low-cost, low-rate wireless standard that was ratified a year ago last spring. It also defines a MAC and a PHY. At the 2.4 gigahertz ISM band, it's a 250 kilobit per second standard. It works with QPSK or OQPSK, I can never say that, spread spectrum. What else about it? Has 16 channels and a 2.4 gigahertz band. Sir?
What is the 5-year lifetime of the battery? Predicated on, is that any use or is that all standard?
That's very specific use. For example, automatic meter reading is a good example of that one, where you're doing basically 1,000 to 1.
At what?
250 kilobits per second. But the Mac was designed specifically so you can actually sleep the systems and wake them up. Bluetooth, for example, is problematic in that regard. Bluetooth was largely designed with a recharge model in mind, that you're going to be carrying something on your person, you can always plug it in and recharge it. So it's hard to make a Bluetooth device that actually has long battery lives. Because the Mac, not because the physical silicon doesn't support it, but the Mac, it's very hard to make the Mac support very low duty cycles with efficient startup. That's also, by the way, why 15.4 chose direct sequence spread spectrum as opposed to frequency hop, because you're synchronized within a couple symbol times as opposed to having to resynchronize on the hopping sequence. The Mac is defined somewhat differently for the sub-gigahertz bands. At 915 megahertz, it runs at 40 kilobits per second. At 868, it runs at 20 kilobits per second. That's mostly due to restrictions in the European standards. I'm chairing 802.15.4b, which is a task group that's working to clean up some of the Mac definition, but perhaps even more importantly, make the sub-gigahertz bands run faster. It looks like we'll be able to do at least 125 kilobits per second in the lower bands. And if you want to know more, go to the IEEE website, IEEE802.org 15 pub TG4. We'll tell you about that whole world. Zigbee is an alliance of over 90 companies right now that are working together to define application profiles that sit on top of 15.4. There are some general purpose ones, but some of the earlier profiles to come out are going to be things like residential lighting and building automation. So there'll be a complete stack. So if you buy a Zigbee-enabled thermostat from one vendor, you know it's going to work with a Zigbee-enabled room controller from another manufacturer. They've been working on interoperability tests. You've got multiple companies now who are proving that their devices can actually talk to each other at the higher levels. And people are expecting to come out with the version 1.0 spec later this year. Questions?
So you want compatibility just at the radio level. You want my radio to be able to talk to your radio.
Yep.
You need anything more than
No, 15.4 is sufficient.
That's sufficient.
That's correct. In fact, Ember has both EmberNet stacks and Zigbee stacks. And the EmberNet stacks are designed to be a bit leaner, not designed by committee, and provide functionality at a smaller footprint than what the Zigbee stacks can do. But the Zigbee stacks aren't bad. I mean, we're getting entire stacks that fit in, well, I know the EmberNet stack fits in about 40K, including application layer code, so you can put the whole thing into a 64K byte processor. Zigbee's probably going to be a little bit bigger, but they're working very hard at figuring out which pieces are optional to keep the footprint down. Here's what at least one marketing group says. It's your typical exponential curve that arcs off towards infinity. But you can actually look at what the different analysts are saying, and everyone is expecting 15.4 and Zigbee both to be fueling this world of wireless embedded networks. This is specifically for 15.4 based systems, including Zigbee and non-Zigbee protocols. But we're expecting a very big growth in building and industrial automation. What's interesting is when we started out, Ember, once upon a time, we've always wanted to be players in multiple industries. And actually, historically, Ember thought going into industrial automation would be a good thing because you can quantify the pain. It's literally $10 per installed foot of control wiring, something that's just giving a thermostat reading in a factory. And for the 100-foot run, that's a lot of dollars. And you can actually replace it with a wireless link, and we can quantify the crossover points where it's more economical. The thing that we didn't count on is how incredibly, shall we say, conservative or deliberate the industrial automation market is. And we literally had a customer that put one of our systems into a trial run for 18 months. And they came back and said, well, yep, it seems to work. Now we're going to fast track it and get some pre-production prototypes out in another 18 months. I'm not making this up. In the meantime, both the building automation and the home automation markets, we've gotten our silicon cheap enough. Remember Moore's Law? We've gotten our silicon cheap enough that suddenly we were able to hit the price points for these much bigger markets. And right now, building and home automation markets are just walking right past the whole industrial market sector, which makes me a little sad, but that's the way it goes, and that's fine. So here's what Ember does. We make chips, we make software, and we make the tools that make it really irresistible and easy to use this and build it into your products. That's really the whole story about Ember. The chip that we're currently shipping is the EM2420. If anyone is familiar with the CC2420 and wonder why the names are so similar, we co-designed it with ChipCon. The salient difference between EM2420 and the CC2420 is licensing. When you buy the EM2420, it comes with the software stack. We are contractually bound to sell the EM2420 with the software stack. And by the same token, ChipCon may not sell it with for use with our software stack. So we're fairly clean on that. As I mentioned, we have bought a chip company, and we're currently developing. Without divulging future plans, you could imagine that the acquisition of a chip company means that we can make more integrated solutions than a chip and a processor, two separate chips right now. That's about it. Just to show that we are not a science project anymore. Do you all recognize what this picture is of? This is a pick-and-place machine for high-speed manufacturing. This is a reel of EM2420 chips. So I can't name that manufacturer, but we are in high-volume. This scene has been repeated in several places. This is really a marketing one. We've been playing with embedded networking sufficiently long that we know all the stuff that doesn't work and has to happen. For example, when I started out on the IEEE standards body, the very first thing I said was, it would be really important if you can offer RSSI or signal strength or signal quality indication above the MAC layer. And everyone said, why do you want to do that? That's a violation of OSI model. And I said, you need it to make good routing decisions. People didn't get that. People did not understand that in 2001. It's pretty well understood now. But the point of this is to say that we've been working in this space for long enough that we've been able to drive the designs, drive the standards, and even stay ahead of what everyone else is doing. We understood the importance of chip-level security, so we wrestled with ChipCon and got them to incorporate the AES-128 symmetric key encryption that's defined to be part of the 802.15.4 standard if you include encryption. It turns out now that's really, really important to customers. People that want to pass medical data around, people that don't want their buildings hacked into for homeland security systems, it's obvious. Power management we've been working very hard on, and as I say, we now have devices that will last basically approach the lifetime of the shelf life of the battery, just by getting the leakage currents down and getting the transport right. Transport layer, we understand what works to make reliable communication. I was talking with Fang earlier and saying, if you think about it, the difference between 99% reliability and 99.99% reliability is on the order of like a packet a week. And you don't get those additional nines until you have really slept with these systems for years. Because that packet a week could be a leaky buffer, that didn't get allocated, or a race condition in an extremely rare case inside your code. So it really takes that kind of experience to shake all these things out of the system. We've recently introduced an over-the-air bootloader, which means that if you upgrade the standards or whatever you want to do, you can actually upgrade these devices without having to go out and touch each one. And if I haven't made myself clear that the thing that distinguishes these networks is that you can't personally pay attention to each node, I have failed you. I'm sorry. But the point is, over-the-air bootloader, that kind of stuff is really, really important. Oh yeah. And this work has paid off. In 2001, when we talked about networking light switches, people said, "You're crazy. Why do you want to network light switches?" And now it really seems kind of commonplace. As a testament to Ember being recognized as a leader, NTS is the company that's working to do certification for 802.15.4 and Zigbee. And they chose Ember's chips and software as their golden reference for their designs. So that's just a nice feather in our hat, but it basically is a result of, we work hard and we care about this space a lot. So here's four, I'm going to go through four companies briefly. Philips Lighting. They make lighting ballasts. Historically, a lighting ballast has been a bunch of copper wound around an iron core and dumped into some tar and put into a metal box. It's not a high-margin item. It's not necessarily very efficient. And in recent years, they've switched to electronic ballasts. And they decided as long as they're leaping into the 20th century, yes, someone's awake, that they should make these dimmable ballasts as well. And while they're doing that, why not make it wireless control? So they're putting EmberNet 2420 chips into their ballasts. And right now, there's a building in Chicago where the lights are controlled through EmberNet, essentially. The switch on the wall is really a battery-powered thin plastic box, which is velcroed onto the wall. They have a problem doing the demo, by the way, because you walk into the room, you turn on the light switch, and the lights go on. And people say, "Where's the demo?" Actually, I take it as a very, very high compliment, because really, as I said, these networks are only doing their job when they're working behind the scenes and you're not aware of them. But the thing this sort of network lets you do, which is really remarkable. So
what is the demo?
Excuse me?
What is the demo in there?
The demo is that, first off,
why do you want wireless switches?
well, first off, so the very first point is there's an initial cost savings. In new construction, it's about $85 to put a drop down the wall with a light switch on it. And that's just on-off wiring, right? There's already a power grid in the ceiling. That's easy. For remodels and retrofits, it's about double that. So it's very expensive to place light switches. But the real savings comes because now, once you have this wireless infrastructure, you can take a motion sensor, a PIR sensor, and slap it in the corner of the room. And when no one's in the room, have it dim the lights. You can take a photocell and put it on the conference room table, and when there's sunlight streaming in from outside, it dims the lights. And you can shave off a very significant amount of operational costs of a building by reducing the amount of electricity you consume in lighting. So you get the initial savings of reducing the amount of wire you have to run, but you get the recurring savings of reducing the power consumption. And that's why it's a big deal for them. What Ember was able to do in this case was really show, here's low power solutions that work and low cost, and you can put them in light switches. We developed code for them specifically, so when you turn on a light, the lights don't go rippling on as you do a multi-hop broadcast, but actually it preloads everyone and says, in 45 milliseconds, turn on. And so everyone turns on at the same time. That's something they wanted to do. We scaled the network to work over hundreds of nodes at a time, and there's really no problem scaling that way. And what they liked about working with Ember is that we could really do a lot of the work with them, because they didn't really, that particular group wasn't really comfortable with RF design. So we're able to provide those services. Question? Who here has been following the RFID space? Okay, good. So, in the Auto ID EPC global taxonomy, there's class 1 tags, which are purely passive, work with backscatter. I think class 2, you can actually provide live data, but it's still a passive one. By the time you get to class 4, you're dealing with active tags that can work with variable data. I would like to propose that what Sensitech makes is, in fact, a class 4 RFID. Sensitech makes temperature logging devices. You throw them into a pallet of grapes or pharmaceuticals or fish, and it travels with the pharmaceuticals or the produce from the time it's packed to the time it arrives at the receiving dock. The way it worked in the past was the receiving clerk, as the trucker, as the big surly truck was unloading the truck, had to go find this thing, haul it out, and dock it, and then say, "Oh, Mr. Truck Driver, I'm really sorry, you got to take that back." That was problematic sometimes. So what they did was they put Ember's nodes inside their temp tail devices. The moment a semi-truck pulls up to the dock, Ember nodes, which are sitting around the loading dock doors, grab the data, relay it back to the receiving clerk's desk, and it shows up on the screen. It says, "This truck just pulled up and the temperature profile is good." So it's really made life a lot easier for them. And they are able to sell a lot more of the device. They have, by the way, these guys have a great business model. They do not sell these, they rent them. They reuse them about 12 times and they throw them out. And on the first rental, they've more than paid for the hardware cost. Part of the reason is because for FDA reasons, this thing has to be in a welded plastic box. So it's purely hermetically sealed, and you don't want battery juice getting out and stuff like that. But they have a fine business, but it's been made even better. So they're talking now about using Ember's technology to go beyond just temperature sensing and get into the broader market of sensing for asset tracking and asset management. What hasn't happened yet, by the way, is the connection between this world and the RFID Class 4 world. So we're actually starting to have discussions with the EPC Global folks to find out what does it take to really define a Class 4 standard. You had a question first?
Sorry for coming in late.
No problem.
Maybe you mentioned that already. What frequency band?
The Sensitech one is a 915 megahertz. Actually, it's frequency agile, 868 and 915.
868, 915.
This is not based on 15.4, however. This particular device. They will switch to that when the bandwidth goes up some. But they have devices that start in Costa Rica and end up in the U.S. and also fly in the hold of an airplane. That's the other thing we had to do for them, is make sure that these devices are quiescent until spoken to.
Have you submitted your spec or your development architecture to the 802.14?
To who?
To 802.15.4? You mentioned that. I thought I heard that.
Yeah, let's see. Have we submitted which?
Okay, so your solution is a proprietary solution, right? Are you planning to standardize it? That's my question. Really.
Oh, I see. This is built on a narrowband radio. It's more that will happen the other way around. I'm actually on the chair of 15.4b. It's more likely that Sensitech will adopt the new 15.4b sub-gigahertz standard when it gets a higher bit rate. No problem.
In the wireless mesh network. So what is your network architecture? Is it like one hop wireless?
So in the Philips one, we definitely do, because these lights are carrying a fairly large area, and
They presume they have AC power right next to them, right? Can't they tap into? I mean,
power. You're saying signal over the power lines?
no. I guess what I'm saying is that the reason to use a multi-hop network would be to go low power instead of save on power, right?
That can be a reason.
Yes, but I mean, in this case, is that an issue, given that
The reason you want multi-hop mesh here is to get the redundant paths so that no one radio is left out due to multipath effects. I'll show you some more about that later. It's really to get the reliability up. And the way this one actually works is that all the nodes in the lights themselves are always powered on. And the light switch itself is asleep almost all the time. So the lights are acting as the mesh, and the light switches are acting as leaf nodes in a two-tiered architecture. So the light switches aren't relaying messages for the light, and you end up with really good power characteristics that way. So these guys can stay asleep for a long time. For this one, you have multiple receiving dock doors. And what we're doing is we're putting readers, not really unlike this, but not in quite such a Smurfy package, just a little industrial package, near the door of each loading dock. And there's no one place you could put a receiver to get all the trucks pulling in. because it's usually buried deep inside the truck, and they're usually metal trucks. But if you put one near the loading dock door, you'll get the signal out from a truck. So we use these actually to mesh together to get the data back to the receiving clerk's desk. So it's a different reason to do mesh, but... Sir.
In the case of a light bulb,
Yeah.
are the lights individually controlled? And if so, how do you handle the case when you have to change a light bulb?
That's a good question, but the node is in the ballast, not in the bulb. The ballasts do get swapped out once in a while, but it's very rare. It's like every 5 to 10 years kind of thing. The bulb was changed more often. One of the things that Philips has done a good job on is they've made a series of provisioning tools. You can actually walk around with a handheld device and say, this light is associated with this switch. I don't really know the details on that. I wish I knew more, but that's actually another great topic of research. Ray systems make sensors for things that go bump in the night. They make radiation sensors, volatile gas sensors, carbon dioxide sensors for use in shipping containers, in multimodal transport containers. I was a little baffled why they made CO2 sensors at first, and someone pointed out to me, stowaways. They're looking for stowaways. So they put these industrial bricks inside the shipping containers, and just on the outside, you can have another Ember node. And there's enough leakage. There's enough RF leakage that you get the signal quite reliably from inside the container to outside. This is a really nasty environment when these containers are all stacked up. But if you have nodes on the outside, enough of them, they find paths. They find their way, and you can get reliable communication out of the shipping container to the receiving crane or the customs office, wherever it has to go.
Pretty well sealed,
It's pretty well sealed, but I've been astonished myself. We did some work with vapor recovery system at gas stations, and they put these nodes inside metal sump pump boxes, and you still get signals out. This is not reliably enough, which is amazing.
So you know the integrity of your mesh given a random distribution of inside and outside, right?
Right.
Before you proceed.
Yeah. But it's still very application specific, right? You can't predict what all the environments are going to be. They recently did a pilot with the Venetian in Las Vegas, putting sensors in their air conditioning plenums. So right now there's a whole live demo of EmberNet working at the Venetian for doing building security. So, yeah, for monitoring. This is the closest we have to like a pure sensor application, I think, in the usual sense. Andover controls. Hotel owners have a problem. Well, there's a few things going on here. This is I think an Amana air conditioning unit. This kind that sits under your windowsill at your favorite Holiday Inn. Hotel owners have a problem in that if air conditioning is left on when there's no guest in the room, or if the air conditioning is running inefficiently, the margins in hotel operations are sufficiently thin that you can actually just eat up your profits pretty quickly that way. So anything you can do to make more efficient air conditioning is a big deal to them. Andover controls, for the people that make the control units for these air conditioners, pretty much a commodity item. And they've designed Ember wireless networking into the air conditioning unit. They're using this for two purposes. One is that there's now wireless controls near the front of the room, so the guest can turn on and off the air conditioner more easily than having to go over and do that as you go out the door. I don't know if they've gotten to the point where you stick your key card, like the European style, if you stick the key card in to turn on your air conditioning. I'd like to say I know that they're doing that. I don't know that they're doing that. But the other thing that they're doing is that it's kind of cool. Air conditioners have a nice physical distribution in a hotel. They're sort of evenly spaced to one another. You can make a very nice mesh out of them and gather the data back at the front desk. And you can turn off the air conditioner when the guest is checked out. And you can also monitor. You have a feed that goes back to the Andover people, and they can monitor the health of the air conditioning. So Andover now can move from selling a commodity controller for an air conditioner to selling serviced air conditioning, and make sure that all the air conditioners are running at proper efficiency. pleasantly enough, Andover was just acquired by Schneider, and Schneider is actually looking at incorporating this kind of technology into a big range of their products. So, question? Yeah, good. So, now for the fun part. These are just a few random muses that we've played with around Ember, and I can talk about some of the implications of them and some of the implications I won't talk about, but this is just food for thought, and we can talk about it. So first off, my biggest advantage going into this embedded wireless network space was that I didn't know squat about RF nor networking when I started out. And therefore, I had to read a lot of texts and learn a lot. And I realized there were different groups who just did not communicate with each other. And there were three important groups. One was internet networking, TCP/IP and all that stuff, generally wired. There was the 802.11 style of networking your computers. And there was the cellular telephony industry. And each group had their own language, their own set of quality of their own metrics for quality and stuff like that. And to this day, there's been a lot that's gone on in the cellular telephony world that just hasn't crossed over into the sensor network world. This is the picture of, I think it's Rayleigh distribution of fading. This is shown time, which belies the origins of this, which is for a cell phone as you're walking. You expect to see fade patterns like that. But in fact, in a static environment like this, even me walking around, and I'm changing the multipath pattern from any given receiver to any given transmitter. And just ordinary changes throughout a day will cause time-varying functions like that to happen all over the place. The texts talk about it in terms of how many dB fading, how much fading you get, and that tells you what your margin is, your link margin. But people rarely take that to the point for packet communication and say, what's the effect on packet delivery rate for a given area? So I did an experiment. This is a picture of a piece of paper, almost 5 inches on a square. Happens to be 1 lambda at 2.4 gigahertz, divided into 100 little squares. And I took one of our developer nodes and positioned the antenna over each of the 100 squares in turn. And I ran a ping test in the middle of the night. I did twice, 12 midnight and 2 a.m. It was a very long night. We since are automating this with an XY table to do it for us. But the point is, as you move just a half an inch, this is a plot of packet delivery rate versus position on those 100 squares. Now I want to show you something. As you move a half inch from here to here, you go from 0% packet reception rate to 100% packet reception rate. I repeated this twice in the middle of the night, and you got the exact same picture both times. Question? What frequency? This is 2.4 gigahertz. Channel 4, which is one of the channels up there. But roughly 2.4. So, again, this is over 4.8 inches, and each of these is a 0.48 inch distance. And you can see these multipath effects going through it. So these are troughs in the due to small-scale flat fading multipath.
Like narrowband radio or?
No, this is actually spread spectrum. Well, I said, okay. 15.4 is a spread spectrum radio. It occupies approximately 2 megahertz out of a 2.4 gigahertz channel, which is really 1/1000th. So it's not really spread very broadly. One demo I love to do, but it's on my other computer. 2.4 gigahertz, as I said, 0.48 inches. In audio, 2.7 kilohertz is 4.8 inch wavelength, and I can play a 2.7 kilohertz tone well within human hearing range, right? And you can plug up one ear and you can move around and you can hear the tone just die. As you can put your ear in a complete null where you just can't hear the signal. And that's really what's going on here. So the take-home point here is that either you're going to have to build diversity antennas and then solve your algorithms so that you know, you essentially have to build 2 full radios, because you need 2 front ends, you actually need 2 decoders. You probably want to do CRC on both of these channels, and then decide which one's good. And most of our customers aren't willing to do that. The savior here is that in a multi-hop mesh, you've got multiple transmitters, you've got multiple receivers. They're actually trying to send the same message through, and if one's not getting it through, the other one is. So one of the precepts behind Ember's style of doing mesh networking is that we do not predestine the channel. Well, we rarely do. We do sometimes. But if you're trying to get a message from point A to point B, you don't name which one of your neighbors is responsible for getting it through. But anyone who is closer to the destination, who happens to be in contact with the destination, is able to get it through. Asymmetry. So there's been a lot of talk about, I guess, papers written on what's called the gray zone, or these regions of uncertainty, or all that. And certainly multipath is going to cause some of that. But what people noticed is that just because node A can hear node B, it's not often the case, or not always the case, that node B can hear node A. And people sort of say, oh, look, there is asymmetry. There exists asymmetry. I decided to actually scratch my head and think about what would lead to asymmetry. Taking out the temporal factors, because, you know, it's quite likely the case that when node A transmitted to node B, they could hear each other perfectly well, and when node B went to transmit to node A, something had changed and they couldn't hear. So that could account for it. But what many bright-eyed students forget about is that radios aren't perfect. And although the power transmission level of a radio is quite tightly controlled, the receive sensitivity is not. A radio will guarantee minimum sensitivity, but it's quite often better than that. On top of that, you have manufacturing variances, which can actually throw in a few extra dB of variance. So this is a picture of floor plan of Ember until next month when we move. I think I was using this node as a central collection point, and we have an Ethernet back channel on all these nodes, so we can gather the data. And so one can send a packet, and you can see who gets the data. And I ran a series of tests. Oh, that's right. I ran tests with each one of these, each pairwise. So sending packets between these 32 nodes or 31 nodes, whatever it was. Many of them heard each other 100% in both directions. What this graph is showing is these are pairs of nodes sorted by the higher packet reception rate of each pair. And that's what makes this part of the curve. But the vertical line, like right here, shows that this particular pair of nodes was 99% in one direction and about 12% in the other direction. And what you're seeing is about a quarter of, maybe a fifth of your nodes that can hear each other at least in one direction have a high degree of asymmetry. So I decided to figure out, what's this coming from? So it's important to understand, first off, a little bit about packet reception rate as opposed to just bit reception rate. This is a slightly unusual plot for bit error rate and packet error rate versus signal-to-noise ratio. It's only slightly unusual, and I've plotted on log linear instead of log-log. But the thing to note is that by the time you're sending a 10-byte packet, right here, there's a 10-byte packet, over a very small range, just over, within 2 dB, you're going from 100% to 0%. It just falls off, bang, like a cliff. When you send bigger packets, it gets even sharper, of course. And so I said, okay, I'm going to assume the following thing. There is some path loss between each transmitter and each receiver, and I'm going to model the same path loss in both directions. But I'm going to model variations in receive sensitivity and transmit power based on real radios to see what happens. Make sense? Yeah. Okay. So I went to our production lab and I pulled out, we characterized, when I said earlier we're not in the business of making modules. We actually do make these things for our developer kits. And when they go through the QA, of course, they characterize them. They measure the transmit power, they measure the receive sensitivity. And so I was actually able to grab the log files and pull out the data for these guys. And so here's a scatter plot of 113 modules where you can see the range of transmit powers and the range of receive sensitivities. Now, if you take what I was calling in the previous slide here, the link pair margin, which is the difference between the transmit power and the receive sensitivity. That is, how many dB of path loss can you sustain and still get a signal through. If you do that pairwise for these 113 modules, these are all 113 pairs collided with each other, you get a bell curve that looks like this, or a kind of bell curve, kind of something Gaussian-ish. So most of them have a. So this is a histogram, right? So most of them have about 89 dB link pair margin, right? They'll sustain 89. Some will do better than that. Some can sustain 90 dB separation. But there's a kind of long tail here where you only get 85, 87 dB. So if you plug that in and use that in a simulation, here's a very simple simulation. I said here's a 30 nodes in a 5x6 grid with some separation. And you choose transmit powers and receive sensitivities for each one of these guys and run ordinary algorithms for path loss models and receive sensitivity and all that. You get a curve that looks like this. And this is much closer to what we're seeing in the real world. So the admonition here is, when you write your simulators, be sure to account for the real manufactured measurement of the sustainable path loss between transmit and receivers. I guess I've been saying all this with an assumption in mind, which may not be obvious to everybody. When you're dealing with a star network, life is simple. You've got a base station and you've got nodes within one hop of that base station. And what happens is a node is either within range or it's out of range. If it's out of range, you tell the person to move a little bit or whatever, but you're not making routing decisions based on whether the signal gets through or not. The network doesn't break. One node might break, but the network doesn't break based on that. In the world of a multi-hop mesh, this kind of stuff can really screw you, because if you're making routing decisions based on that measurement and the other node cannot respond to the first one, there have been many bad algorithms written not taking this into account, and I should know because I wrote at least 2 of them. So this is important. Also, not talked about much. If you're a hardcore RF geek, you probably understand this, but you're probably not the person who's writing the networking algorithms. People tend to look at bit error rate, and they can know how to convert that into packet error rate to decide the probability of receiving a packet or not. Well, that's wrong. Because before you can actually receive a packet, you have to synchronize the packet. You actually have to detect there's a synchronization header and a starter frame and, get the radio happy. Now, what's interesting is you can go to Sklar and look up the bit error rate curves for a radio given, particular modulation scheme with a particular path loss and signal noise ratio, all that kind of stuff. And you can get very detailed curves for what that is. What you can't do is ask the radio manufacturer for the state machine inside their radio that's trying to detect the starter frame. That is not generally available in textbooks. I'm not even sure our own engineers could, tell us exactly what the bit error rate, or, what is the synchronization success rate as a function of signal-to-noise ratio. So that troubled me for a while until I realized it's not too hard to compute it. So here's the probability. Here's the decision graph for whether you get a packet or not. First you have to synchronize on it, and then you have to not get any bit errors. in the packet. So this number is visible, but the other numbers are invisible. This shouldn't really astonish anybody in a big way, but the secret then is that you simply send a bunch of short packets and look at your packet success rate, and send a bunch of long packets and look at your packet success rate. And what you've got is two equations and two unknowns, and you can back out what's the probability of bit error rate, and from that you can back compute the probability of sync failure. Now this is interesting stuff for a few reasons. Capture effects are important. Some radios have a characteristic that if I've latched onto a packet, it takes another signal considerably stronger than the one I've latched onto to cause a bit error. And if you think about this, that fact is going to affect the algorithms that you design. Another example is if you're sending short packets and you want them to go, let's see, if you're about to send a long packet and you're sending it to a nearby neighbor, it's kind of useless if someone far away synchronizes on it when it's very likely they're going to get a bit error rate and knock out the packet anyway. So you'd rather they not synchronize on it in the first place. And it's kind of interesting because you have a little control over that. You can actually change the length of the sync preamble. If you put a long preamble on it, the radio is more likely to synchronize. If you put a short one on it, it's only going to synchronize if it's in a fairly noise-free channel. And you can actually exploit that to get better performance, because what you can mean is if I'm about to send a long packet, I can put a short preamble on it, which means that only radios in fairly noise-free channels that were going to get the whole packet with bit error in the first place will successfully get it. And you can actually free up some of your airspace this way by doing that trick. So those are the three kind of weird, cool, technical things that we've been mulling over recently. Starting to, yeah. This last one we haven't done anything with yet. One thing we really need to do is characterize how strong the capture effect is for the different radios that we use. Because that really does have effects on how you design the Mac, for example.
We want to talk to the TinyOS people who also be looking at some of these asymmetry problems.
Well, this is inspired that I wrote each one of these things after coming back from successive nest retreats.
If there's some interaction to see whatever. But I agree that some of these are really interesting and unique to these deployment problems. So the asymmetry of the ring was interesting. It's been observed by many people. And, you seem to be making an assertion that current routing protocols don't take that into account. That's not true. I can think of several that take that into account.
Most recently they do. It's the simulators that bother me. People have said, oops, these algorithms don't work, but now we observe symmetry. And I'm really just making the argument that the bulk of asymmetry can be attributed to manufacturing variability in radios. And that simulators you should be able to get a bunch of radios from your favorite manufacturer, characterize them all, and plug that variance, that distribution into your simulator. And I think it will really help you a lot.
The other possible source of asymmetry, and I guess you were doing standard measurements, it doesn't matter, is the differential traffic in neighborhood of features.
Right. Yeah. No, I was doing one-way traffic just to characterize this. Otherwise it gets too crazy to describe. But yeah.
So at some point, this asymmetry can cause the link to completely stop functioning in either direction, right? Because somewhere at 802.11 you need ACKs for every packet that you send.
Right.
And so if the ACKs can't get through them, then the link stops working even in the direction that it's.
You can design algorithms though that if you can get acknowledgement to another channel. Yeah.
I'm just saying, like 802.11 as it is today.
That's right.
Do you have a sense for how often that happens, like because of asymmetry that...
Yeah, this is what's interesting. I should have drawn the picture, but this is saying, as many as a third of your nodes are subject to some amount of asymmetry, right? Because these guys hear each other 100%. These guys out here hear each other 0% in both directions. And here you're getting, this is just all over the map, right? If things really change with distance in an even way, the picture I'm about to draw would be true. But please forgive me. It doesn't really work this way, but it's an easy way to think of it. If you have a random distribution of nodes, sort of, how do I say, an even distribution of nodes, but random, right? Over space. And there's some number of nodes within the 100% circle here, right? Like, these guys all hear each other really nicely. So from this point of view, this node, you have good connectivity with all those nodes. And outside of another range, you're at the 0% in both directions. So you don't hear anybody outside this range. But within this area, you can show that the size of this annulus, the area of this annulus, is approximately equal to the area of this inner circle for certain conditions, right? Which means you're going to have as many nodes that have this high degree of asymmetry as you have good links to. So this is really only a problem in the multi-hop mesh network because it's hard. It's very hard from the point. Here's the thing to remember: from the point of view of this radio, it's very hard to distinguish. I'm getting 100% packet reception rate or a good signal-to-noise ratio from this radio, and I'm also getting 100% from this radio. You don't know how far away this radio is or how far away this radio is. All you know is that you're getting 100% reception rate from them. What you may not know is that this guy hears you very well and this guy doesn't hear you for squat. So in the context of a multi-hop mesh, this becomes very important. In the context of an 802.11 network, it's not so important because you're not making routing decisions based on that.
So why do you make routing decisions at the MAC level?
Excuse me?
Why do you make routing decisions at the MAC level? Why not do what 802.11 does, just run in the ad hoc mode, leave routing decisions to players above you?
We don't make routing decisions at the MAC layer. I'm sorry, did I say that?
Yeah, you seem to say that 802.11 doesn't make routing decisions, which implies that you do.
Oh, I'm sorry. A star topology such as built on top of an 802.11 network with an access point and a base station doesn't make routing decisions. It's you find the nearest base station and you talk to it, and that's it. In this world, you're trying to decide which one of your neighbors is supposed to relay a message for you, and that happens well above the MAC. That's a good point. So I apologize for confusion. Want a demo? Here we go. So this is a demo based on what we call Ember Studio. These are Ember's evaluation nodes. When we're starting out this business and you're in a commercial company and you hear about this thing called, mesh networks or wireless networks or sensor networks, it seems very strange to your boss. So you have to convince your boss that, this little startup company in Boston knows what they're doing. So you convince them to spend $4,000 to buy a dozen little cute Smurfy hockey pucks, and you scatter them around. And did I push the wrong button? So we made this evaluation kit specifically so I'll watch this come up here this time to convince the bosses that this wireless network stuff worked. What's really happened since then is most people believe it works and they go straight to the developer kit instead. So let me see what's going on here. Oh, that's why. Yes. I have 2 copies. There we go. Okay. Did I leave him on? There are not supposed to be any nodes up right now. So I'm going to go pull some pins out here. I just hadn't updated yet. So each of these guys is a 15.4 compliant radio and a bunch of other stuff in it. We put in a cute package so you can see the guts of the thing, so you can show people it's real and all that stuff. We put a button on it. We put a 2-axis accelerometer in it. We put a beeper in it. Put a temperature sensor in it and a battery sensor. And I remember checking the battery levels, and I think one of these is going to die fairly soon, but hopefully they'll stay long enough now. So what the colors are showing you is what's the, there we go, what's the link reliability in each direction. So green is 100%, blue is slightly, like, 95% or something like that. It's not a particularly interesting topology right here, right now, because it's pretty much everyone can hear everyone.
The asymmetry is the color.
Yeah, that's right. So already you're seeing some asymmetry. One of the things that we do is kind of cool in this demo is how you do provisioning. So I want to associate that node with this node. So I pushed this button and held it for a moment and say, okay, I've now associated these two guys. And I think, is it this one? Yeah. So when the accelerometer goes, it sends him a note, says, go. And you can actually see node parent. Here it is. Thank you. So it shows that the guy on the podium here is paired with that guy over there. And, of course, pairing can be sort of arbitrary in that I can pair this guy with, I need my exercise. This guy. And, oh, a jumper. This guy. Put him on the thermostat instead. And when I go back and unpair him, or take him out of pairing mode, what did I say about unattended networks? Did I do it? Huh, no, I got one. Oh well. But it should be the case that, yeah.
So which two are you? That one?
Yeah, that one is talking to the one on the thermostat.
That one's still alive after 4.
Yeah.
Does the layout that you display here have anything to do with the relative locations?
Before you came in, I very carefully positioned them so they'd be in the right place. This one should be actually right here. Yeah. So the blue one in the middle, all the nodes, I should emphasize, all these nodes are the same. You can plug a serial cable into any one of them and use it as the gateway. But it's really just a gateway. It's not a network controller. And so all this information about pairing and stuff doesn't depend on the gateway to make it happen. It's a really decentralized network, if you will.
How much traffic is going on right now?
Right now we're sending, we're doing updates, I think like once every 5 seconds or something like that. You can change the parameters on how much network traffic you do.
Do you ever have a mode on that shows?
Yeah. So, yes.
So I have a question. So this is the radio here is what? The Zigbee radio?
It's a 15.4 radio. Yeah.
So what is special about it? Because we run a network like this upstairs with
Sure.
off-the-shelf PCs and off-the-shelf wireless cards, nothing special. It's all done in software.
Right.
So I'm wondering what's special about it?
Okay. Radio chip itself in quantity is $3.50 with the stack included. And, excuse me?
The networking stack all the way up to TCP?
Up to application layer.
Okay.
It fits in about 40K of RAM on a processor. Doesn't need a PC, right?
Okay.
So, I'm not sure I understand your question.
I'm just wondering what is the key technology here? Enabling mesh networks is not that hard. You can do it over 802.11. We do it every day. I'm just wondering what is the key technology that Ember is providing here?
How big is your stack?
I don't know. We never tried to optimize it. That's the right answer.
How big is your stack?
We never tried to optimize it.
Roughly. Could you give me an order of magnitude? Because I'll believe you can get it down by a factor of 10. I won't believe you can get it down by a factor of 100. How big is your stack?
You never tried to.
You're not answering my question?
Okay, all right. My routing protocol fits in under 100K.
Okay.
Yeah.
So how small do you think you could... So we're talking about the entire application. We're talking about the radio adapter layer. We're talking about the MAC. We're talking about the routing layer. We're talking about the transport layer. We're talking about all the way up to the application.
At transport layer, we just get whatever,
Right.
We connect to Windows. We don't do anything below
Right.
OIC.
Right. We have to fit it all into... We have to fit it into micro. Otherwise, our customers won't buy it from us. So that's really what we're doing. We're focusing on the tiny. And that's really what the value is here. I'm sorry it's not actually a real mesh here, because it'd be more interesting to watch. But, you can do things like, let's do a trace route test. Trace route will be very, very boring today. Let's see if we can have a hope of getting it. Let's get this guy. So I want him. Talking to, let's say, him. To answer your question, we're sending packets every 250 milliseconds right now, 25 byte packets. We're sending 100 packets. It's going to run for a while, and it'll report back when it's done. And sadly, we'll probably report that it got 100% in both. 100%. What's interesting is you can actually run traceroute in this case. You'll see what percentage goes to one route and what percentage goes to another route.
Can you remove an antenna?
I was told it's not good for the radio. But this probably isn't good for radio either.
I got a folded set. I mean, that's just my experience. Yeah. I'll just do the setting. Just so you can see this. Interesting, we're still getting. I would suggest that you take 4 meters of time in a while you actually setting this. Yeah. Let's back her up again.
So basically all this